So last time I reviewed the growth and reconstruction. They're associated to a scheme X of the kind we're studying, quasi-projective over field. You have two growth and reconstructions. One is the growth and group of vector bundle. And on the other hand, we also had this other one, the growth and group of coherent sheaves. And the point was, this object was a ring, commutative ring, this object is a k naught x module. Both of these operations, the ring, the multiplication and the module structure, come from tensor product of vector bundles. So come from taking F to E tensor F, where for example E is coherent and F is coherent and E is a vector bundle. So of course, if I have two vector bundles E and F, this is a multiplication. If F is just coherent and E is a vector bundle, multiplying by E makes sense. So here this is a ring, this is and this has a module structure. And then finally, every vector bundle is of course a coherent sheaf. So there's a map K0x to G0x, which is K0x linear. Both this being a ring and that being a module, both of them have an action of K0 and this is compatible. It's just saying essentially it's the same formula defining both the multiplications. So all these are, we're not saying anything about it. It's just a map. But the reason we introduced this K0 is we were interested in trying to see if Fy to x is a morphism of non-singular varieties. We were trying to see whether we can write a proper push forward map from K0y to K0x. And the assertion was that we can do it if x is non-singular. This we're not sure. But what we could construct is there does exist F lower street from G0y to G0x, given by sending the class of F to the class of its total higher derivative, so to speak. A kind of Euler characteristic along the fibers, so to speak. And this was well defined. This we could always do. So it was important to know something, proposition, the so-called resolution property. That if x is non-singular, okay, then the natural map K0x to G0x is an isomorphism. Because then if we had this property, then if I have F y to x proper, where x, y are non-singular, then I can look at the following composition. I can go K0x, this is isomorphic to K0y, this is isomorphic to G0y. There I was able to define a push forward, G0x. And then there's sort of the inverse isomorphism to K0x. So this allowed me to write a proper push forward in the non-singular case. And this was the strategy. So this is a kind of important property, this resolution property. So I want to discuss the proof of that. So how does that work? So proof of resolution property. Well, after all, X sits inside Pn as locally closed. That's what quasi-projective means. And further, any F coherent on X is of the form I upper star of Fpn for some coherent. Right? So both these together imply that any coherent F is a quotient of a locally free sheaf E. So for any F, it's possible to find a locally free sheaf E and a surjection E to F. Using the context, in fact, the way to do it is you can even take it to be OX of minus A to the power B. You can even find an E of this special form, which is a direct sum of line bundles. The reason is, this is just saying that FA is globally generated by a set of B sections. Right? Saying that if the sheaf after all comes from projective space, any sheaf on projective space has the property that some twist is globally generated. So restricted to X, it's still globally generated. And it's coherent. If I have a set of sections which generated, finitely many of them will do. Some kind of Noetherian property is standard. So you can do it like this. That I have to argue now. That's the point. So what you can do is let D be the dimension of X. Then what I can do is I can write certainly an exact sequence like this: FD, ED minus 1, E0 to F to 0, where all of these are vector bundles. And this is just the kernel which appears at the state D, whatever it is. And I know then that this is coherent. Now let me look at the stalks at a point X. So choose a point X in X and consider the stalk. That's a sequence of finitely generated modules these are all modules over OXX. But now the point is X is non-singular, so this is a regular local ring. Because there are various, there's a standard definition of regularity, Noetherian local ring, where maximum ideal is generated by D elements, where D is the dimension. But there are other characterizations of regularity. This, or a theorem about regular local ring that you prefer. Various people, I think it's sometimes called Auslander, Buxbaum, said one attribution is like this, but depending on the language in which you are attributing, maybe it's a subset or a superset. This is one type of attribution, would imply that the homological dimension, projective dimension over OXX of any finitely generated module M is less than or equal to D equals dimension. x. Dimension of OXX actually might be smaller. So it's only less than or D. That's the theorem. Yeah. And then you have to do some argument to why, once you can do it for the residue. I mean, that's standard homological algebra. I'm not going to get into the details. But then the upshot is, because of that thing, this is actually a free OXX module. So FD is a coherent sheaf, each of the stalks of which is a free module. These things imply, so these two properties, coherent plus free OXX module. So FD coherent plus FD x is OXX free for all x. Together implies FD is locally free. Just for amusement, let me see. I want to write down a counterexample where I drop this and I keep this and finitely generate this. The example is the following. I mean, there are lots of examples, but let me give one which I find amusing. I was sitting in some lecture by somebody who had, sorry? Yes? I'll give an example where it's free rank 1 and it's still false. Exactly, I sat in a lecture by somebody who was doing some expository and they claimed this and it was wrong. So I gave them an example out of it. So my example is not varieties over field. X equals spec as the integers. F is equal to m tilde for some module over the integers. In other words, M is an abelian group. M equals all rational numbers A by B such that A, B in Z, B not equal to 0, B square free. This is an abelian group, all rational numbers with square free denominator. This is certainly not finitely generated, so F is not coherent, so there is no chance of it being locally free. Okay? It's not even coherent. The module is not finitely generated. But if I localize at any prime number, spec Z, the points are the prime numbers. Once I localize the prime numbers, only the power of P matters in the denominator. The other primes don't matter. So M localized at a prime number P is just Z localized at P times 1 over P. So it's free of rank 1 at every prime. And of course, rational numbers, it's a very one-dimensional vector space. So without finite generation given to you globally, it's wrong. You have to be careful about blindly applying some of these things. Just a little example. Then you can use this to manufacture other examples. You want to construct a morphism f x to y of schemes where everywhere locally, at every point when you localize, the fiber is the affine line. Is the total space a line model? False unless you assume the total space is non-theoretic. Things like that. It's a very simple example. It's very easy to remember this once you've seen it once, is my feeling. So I thought I should write it down. A quite distinguished mathematician was giving lectures and he made this mistake. So it's an easy one to make if you're not paying attention. So that it's good to remember. Anyway. Right, so this proves that every coherent sheaf has a resolution. So this implies our resolution proposition is proved, and therefore it follows that proposition immediately implies that K0x to G0x is surjective. Take any f, write such a resolution. The class of f is the alternating sum of these classes. These classes all live in the image, so f lives in the image, right? So therefore it's surjective. Now I want to actually say it's an isomorphism. So I want to go the other way. It's natural to try and do something like this. Start with an f, a generator. Just choose a resolution and then attempt to map. So what about G0x in the other direction? I'd like to do the following. I'd like to start with an f and send it to class of E0 minus class of E1 dot dot, where I choose such a resolution. But then, of course, the question is, why is it independent of the choice? So that requires a little discussion. Let me say a few words about that. I want to make one trivial algebraic remark and then use it repeatedly to do everything. So the remark is the following. Suppose I have G suppose I have a coherent sheaf G and maps to G prime and G double prime. And suppose I have E prime to G prime surjective and E double prime to G double prime surjective. Suppose this data is given to me. Then I claim there exists E with a surjection and maps to both of them. So let's convince ourselves this elementary statement is correct. Basically, what you do is you take the fiber product of these two, so call it E1 prime. Then there's a map to G. There's an E1 double prime coming from this fiber product. Sorry, from this fiber product. So of course that maps to G. This is surjective and this is a fiber product, so that's surjective. This is surjective and that's a fiber product, so that's surjective. The fiber of these two is an E2 which maps onto both of them. And then I can write E2 as a quotient of an E. I mean, I'm just giving you an argument. Yeah?
Those intermediate
Are not vector bundles. Good point. To emphasize that, in the middle I took non-vector bundles. Kapil is saying it's bad to use E. Pedagogical error. Yeah. Okay. I hope it just follows from usual nonsense. So the basic statement is that given a diagram like this, with just some maps, I'm not asserting any properties of these maps, they exist. And here, if I had vector bundle, then the assertion is there exists a vector bundle in the middle with just maps again with no particular properties, but this map is surjective. This is what I assert, and I've given you a sketch of an argument. Just do obvious things each time, keep going back as much as you can. In very fancy language, just forget this, take the limit of the diagram, that's a single sheaf, write that as a quotient of a vector bundle. Remember, those who know about more general limits, that's what I've done. I just took the limit of the diagram, the inverse limit of the diagram. Okay? I want to find something which maps to everything in the diagram. There's a universal way of doing it, call the limit of the diagram, whatever it is. It always exists. The category of such bound finite diagrams in reasonable place have small limits. So there always will be a limit. What I want in addition is that that limit guy, whatever it is, surjects here, but that comes from the specific data. The limit has the property in this case. Right? Anyway, okay, so I can do this. Now clearly if I can do this, I can inductively build up the resolutions, you see. Suppose I have two resolutions of, so let's assume we give ourselves two resolutions. I have two resolutions. I'll start with this diagram first. And then here I'll put E0 double prime mapping and here E0 prime mapping. And then my lemma gives me an E0 which maps onto F and maps to both of those things. Now I'll have some kernel, whatever it is. Just because the diagram commutes, there are maps like this. Right? So this I'll get. Right? But now here I'm given something more. I'm given E1 prime mapping onto K1. I'm given E1 double prime mapping onto K1 prime. So this diagram is of the type appearing in my lemma. So I can find an E1 mapping to both of those and mapping onto this, and so on. What will all this give me? In the end, I'll be able to construct a diagram of the following type. Let me just explain that. Let me be a little thing here and just put FD to flag the same thing which Kapil was saying earlier. Okay, I'll construct such a diagram where these are all given to me. This is just take the kernel of whatever you got there. That's my definition. Certainly such a diagram I have. Now I'll go back to this business here. Hochslander Buchsbaum said. That tells me that if up to here I got vector bundles, the last thing is automatically a vector bundle for homological reasons. So FD can be erased and I can put E. That's a vector bundle. So what I've managed to do is I've managed to show if you have two resolutions by vector bundles, I'll construct a third one which maps to both of them compatibly. Then I can remark the following. Suppose I have E dot to F and say E prime dot to F. Two resolutions by vector bundle and a map. Now forget the F part and just look at this part. This is some map of complexes of vector bundles which induces isomorphism on the homology. There is in fact only one homology in each case, F, and F to F is the identity. So this is a quasi-isomorphism. Iso on homology. So this implies the so-called mapping cone is exact. Is an exact sequence of vector bundles. This implies a relation in K0x, which is, after rearranging, just saying that sum minus 1 to the I class of EI is equal to sum minus 1 to the I class of EI prime. Okay, I want to try to write down exactly what is the mapping cone. There's some indices there. I don't want to get into all that. Whatever it is, it's some bounded complex of vector bundles and it's exact because mapping cone has the property that the given map of complexes, there is a long exact sequence involving the homologies of the individual complexes and the homology of the mapping cone. So if the map, and that's a long exact sequence. But if all the homologies of the original two complexes of maps are isomorphisms, from the long exact sequence, the homologies of the mapping cone are all 0. Right? So that's saying homology of 0 is the same as saying it's an exact sequence. When you have an exact sequence of vector, that's certainly a relation in K0. You have to figure out that indeed, if you write things down carefully, in the end the relation boils down to this, which is anyway what we expect is going to be right if our theorem is right. So now I can compare both these presumed K0 classes which I got from the two resolutions with the K0 class I got from the third one, and therefore it's independent of the choice, is what it says. This is in fact well defined. Independent of choice of resolution. This is elementary algebra. Of course, it's also the case from the same lemma used repeatedly that if you have a, well, a version of the lemma anyway, that if you have a short exact sequence, so maybe it's a different lemma I need for that. If you have a short exact sequence 0 to F prime to F, Let me see. Let me not see where to write it properly. I'll just do it here. So I claim if I have a resolution f prime take a short exact sequence like this, then I claim there is a diagram like this. In fact, there's a standard way of attempting to do it where these things become direct sums of the terms. These vertical things are split. You have to do a little work, but it's correct. It can be done. Anand proved this? You did? Okay, in any case, this is correct. If people have doubts later on, I'll write something down. But this is very standard. The other one is not unstandard in some sense, but I mean, it's simple to just write down an argument, is what I thought. Yeah. Yeah. No, that's not allowed. Because when you do short exact sequences, you will have. Exactly. So you will be saying some relation holds in the ambient category, which is no use for me. I want it only involving vector bundle. That's the whole point.
But ultimately, when you have a long exact sequence of vector bundle with 0,
yes.
Then the breaking up into short exact sequences.
Of the mapping cone would do it. Yeah, exactly. No, that I'm taking for granted. I'm just saying if the original sequence I try to do something, I'd be in trouble because then I'll go out of the category of vector bundles. So I'll get some f equal to f and k0 and g0, which is no use to me. Yeah. So I need the fact that if you have a short exact sequence, it is possible to construct a diagram of resolutions. And if you make these choices, then it's of course the case that whatever assignment I did to f prime and to f double prime, the assignment for f is the sum of those two in k0. I have to argue something, yeah. Huh? No, we have to prove this lemma by whatever method. Let's go into it afterwards if people have doubts. So then that tells me that a priori what I did, I just took an f, a sheaf, and then I argued this is well defined. This would say that if you have a short exact sequence of sheaves, the class which I associate by this procedure to the middle is the sum of those two classes. Therefore, by the growth reconstruction, I can think of this as a map from here to here. Okay, I have to check that also. Not just on the generator, I have to check on the relation that's satisfied. That constructs, therefore, a well-defined homomorphism like this. This homomorphism, of course, I can compose with the original homomorphism G0x, which remember was surjective. So, or maybe I should have done the other way. Let's look at this. Now, if I took the class of vector bundle E here of course it went to the same E, and the resolution is E equals E. And that's an obvious resolution, so that's E. So this composition is the identity on a set of generators, namely the E. Therefore, of course, it's the identity. But this was surjective, so both of them are isomorph. Okay? Elementary arguments. Right, so that constructs for me, therefore, the proper push forward in the non-singular case. And then I can set up the question of whether such and such a diagram commutes. So therefore, if I have f y to x proper, x y non-singular, but for my diagram at the moment at least I'm going to, write it like this. There is a diagram with these arrows, and it's a natural question: does it commute? So the Grothendieck-Riemann-Roch theorem is that. Okay. So before looking at Grothendieck-Riemann-Roch, let's look at Hirzebruch-Riemann-Roch, which is the case y x equals point. And y is a variety. So y is a proper variety, okay. So what is the diagram trying to say in that case? It's saying go from k0y by the Chern character on y to the Chow ring of y with rational coefficients. And then there's a map f lower star to the Chow ring of a point with q coefficients. But this is just Chow, this is Chow upper 0 with q coefficients, which is just q times the point. And here, k0 of a point is just z. This is point is just spec k, right? And so what is this map here? So the map from here to here is the Chern character on a point. There are no higher Chern class or anything. This is just the inclusion of z into q, the natural inclusion. And here, if I took the class of a vector bundle E, or a coherent sheaf in general, this would map to the Euler characteristic of E on Y, considered as a element in K0 of point, but K0 point is an integer, so it's just the underlying integer. Right? For identification of K0 of a point with the integers, sends a virtual vector space to its dimension, which could be an integer. Right, so in other words, we're asking, give a formula to talk about commutativity. Basically, so what is this projection here? This maps onto Chow dimension y of y with q coefficient, the Chow group of points, and then there's a degree map on 0 cycles. And the question then is there a formula? To what extent, what is the relation between chi of the sheaf and the degree of the top component of the Chern character? They're not equal, right? Even Riemann-Roch curves and so on, there were some terms involving the tangent sheaf. So the general theorem, so-called Hirzebruch-Riemann-Roch theorem, would say that you modify that diagram in the following fashion. Even for curves, it's not correct, is what I'm trying to say. So I'll have k0y to Chow, let me now say Chow dimension y of y with q, and here I will take Chern n, Chern dimension y, so to speak. Don't take the whole Chern character, take only the part of it which lands in the right dimension.
Yeah, you just take the trivial sheet
Right, you're thinking I took the structure sheaf chi is 1.
No, that side the image is 0.
That side the image is 0. So 1 is certainly not equal to 0. So therefore the formula cannot be correct.
Well,
Chi may not be 1. You're saying.
But
There's no reason chi is 1. Chi can be lots of different things. Yeah. P1 itself is false is what Kapil is pointing.
Classical formula for Todd is to say that it is the Euler characteristic of integer. Come, what I'm saying is
Todd figured out what it should be by taking projective spaces and doing all the computations. Absolutely. That's what I was told. I heard, yeah. Right. So then the correct assertion, commutativity assertion is not this one, but you have to multiply by some class Todd of f, let me just write it like that, which is some isomorphism. And then multiply and then take the degree and, so I should be careful. If I do it like this, I'll have a problem. There's no multiplication I can do at the level of Chow dimension y. This doesn't work. So I'm forced to go back to the full Chow ring. Here I multiply by something which I'll call Todd of the map F, which is an isomorphism, but not a graded isomorphism. It mixes terms up. Then I project onto Chow dimension y, yq, and then I take degree. Right? This sort of a formulation is okay for curves and surfaces for some suitable class. And the Hilsebrook-Riemann-Roch theorem says there is a formulation like that in any dimension where tau class of something, maybe of the tangent sheaf is our guess based on earlier examples, should be the right thing to put here. So Grothendieck-Riemann-Roch is a generalization of that statement. So let's do that. So the Grothendieck-Riemann-Roch theorem, let me state it in two equivalent forms. The assertion is there is a commutative diagram. You just write tau of f. And then here I take f of star. But now what is tau f? Let's take tau of y of the tangent sheaf of y minus I can write like this, tau y of f upper star of the tangent sheaf of x. That's of course also the same as tau y of tangent sheaf of y divided by f upper star of tau x of the tangent sheaf of x. Tau is multiplicative, and so when I put minus, I'm dividing by something, and tau is functorial, so it's this. Difference. Tau of the difference, absolutely. Quite right. In fact, that's what's written in my notes. In this case, it's correct. I just copied it wrong. Take the virtual vector bundle, which is tangent bundle of y minus the class of the pullback of the tangent bundle of x. That's some element in K0 of y. So it has a tau class by our formalism. And that tau class is the ratio of the two tau classes. And the tau class is also functorial, so I can pull the f upper star outside. So the assertion is this diagram counts. And each of these elements is a unit in the respective place. Notice also, I should have said this, f lower Shri G0y to G0x is K0x linear. I should make this remark. What does this mean? Remember, there's a map f upper star K0x to K0y, ring homomorphism. I should have said this too. It's not merely a ring associated to X, it's functorial, contravariant functorial for maps, like cohomology, like Chow rings in good cases. K0 is also contravariant functorial. And it's compared with the ring structure. The ring structure is also functorial for maps. That's because vector bundles pull back, tensor, short exact sequence of vector bundles give me short exact sequences. Tensor product goes back to tensor product. So this is a ring homomorphism.
X is equal to possible.
Yes, in my in my things between non-singular, quasi-projective for the purposes of my lectures. Though in the end, the theorem it's not required. This is a remark I made right in the beginning of the course of lectures that I'm restricting to the quasi-projective case because of technical reasons. The theorem is correct without that. It's not so easy to prove in the proper but not quasi, things like it's proper but not compact.
Suppose before you made that as a difference of tau.
Yes. Yes.
It was tau or some
Virtual element, yeah.
So suppose it was a smooth one.
You could attempt to formulate the taught part will work.
The one was
Well, there's a map K0 to G0. I believe there is a formulation like that, yes. I don't want to commit to it just here standing on the board without thought, but whatever the facts are along those lines are there in Fulton's book is of course a safe answer. Yeah. So whatever the answer is, it was well known long ago, it's just off the top of my head. Right now, I don't want to give a wrong answer. It looks plausible what you say. I believe it's reasonable. It doesn't require. Sometimes even without that condition, it's still possible to make sense of this difference, even though the map is not smooth in some other fashion, maybe you can write. So people are
dependent complex will have tau.
possibly there again. I don't. Yeah. Then you have to worry about that. Yeah. But in any case, Nitin, along those lines, anything you can think of that kind is already answered in the literature. I can't tell you the answer right now, but you have to ask the right people. Send an email to Illusi. He'll give you the thing which they arrived at after, as somebody says, wrestling with formidable technical difficulties. So you can find out the last word from him. Or even better, write to Gaber. Probably something even more general will emerge. Anyway, I'm not going to think about it. Right. So the point is, this is a ring homomorphism. Therefore, anything which is a K0y module is automatically a K0x module thanks to the ring homomorphism. Right? So this was a K0y module, therefore it's also a K0x module. So both the sides are K0x modules. It makes sense to say it's K0x linear. This assertion makes sense. Why is it correct? The reason is what's called the projection formula for higher derivative images. That says that if you take E tensor Ri f lower star f, this is naturally isomorphic to Ri f lower star of f upper star E. Tensor f. This would be tensor Ox and this would be tensor O1. Because this property is true for individual higher direct images, if I have some expression like alternating sum of Ri's and multiplied by E, that's the alternating sum of of these things, which is what you get by applying the E upstairs and then taking derivative.
So the extension is in the derivative.
You could view it like that. Yes. Okay. That's good. That tells me that in any formulation like this, all the terms in question are modules over this K0. So all four terms in the GRR statement, DRR diagram, are K0x modules, and all maps are K0x module maps. So here I am using the fact that the Chern character on X, a map from K0x to the Chow ring, is again a ring homomorphism. So anything which is a module over the Chow ring of X is also a module over K0x, thanks to the ring homomorphism. So this K0x mapped to all the other rings. So whatever other module structures there were respectively can be all viewed as K0x modules in particular. I claim all the maps commute with K0. That's because here it's saying there's a projection formula That's this projection formula. There the K naught X structure was through the Chern character. So there I have the projection formula for cycle and Chern classes, cap products with Chern classes and the like. So that, I mean, its projection formula is valid for general elements. So in particular, it's valid for elements coming in the image of the map. So it's okay. I can use this to multiply everything by some unit if I want and see what happens. So that allows me to reformulate the thing in the form which many of you might have come across the theorem before, which is saying that don't take the ring homomorphism, the Chern character, from K naught y to chow star y. Let's modify it to a K naught y linear map, but which is not a ring map, not compatible with the multiplication. K naught y to chow star y q by just alpha goes to Chern y alpha multiplied by tod y of ty. The ty on this side, this tf, ty appear in the numerator, so I multiply by tod y. And then the assertion is that this diagram, so GRR equivalent formulation, K naught y to chow star y q given by it just says this commutes. So the diagram does commute, but don't take the Chern character. Take the Chern character multiplied by a unit. You lost the ring property, but you still have the module property.
And as K naught module, K naught X module.
Yes, well, all the maps are K naught X linear, and the diagram commutes. And then automatically it's a commutative diagram in the category of modules. Okay, so of course, there are two formulations. It's pretty clear they're equivalent with the module structure because this elements of the form tod class are units. I have to come back and discuss the tod class again properly since we had some mess. I'll do that in a moment. But whatever it is, tod class is 1 plus higher degree terms. So anything like that is invertible in all these rings, right? Because the chow ring is nilpotent. I mean, the higher degree graded, I mean, it's a ring with only finitely many graded pieces. So anything which is purely a sum of terms of degrees greater than 0 is a nilpotent element. And so something like 1 plus higher degree terms is nilpotent, is 1 plus nilpotent, which is invertible, right? So I multiply and divide and the like. So now, of course, this formulation is very nice for the following reason. It's visibly compatible with composition of maps. All I'm saying is given any y, there is some operator, and I'm saying it commutes with f lower star. So if I have f1 and f2, and f1 lower star it commuted, f2 lower star it commuted, obviously it commutes for the composition. Yeah?
With your F lower star there,
Yes?
you graded.
What do you mean? No, this commutativity is not about one graded piece. In the end, by the way, of course, here everything in sight, I mean, how to put it? The targets here are rational vector spaces. I can put a Q here if I want. It's the same theorem. I haven't lost any information by putting Q. And later on we'll see this is an isomorphism. We'll see this later. This is not obvious now, but after the fact. So indeed, all the graded pieces are involved. And you've got to involve them all somehow to take, and somehow that's the extra, if you like, which is sort of there in the Grothendieck-Riemann-Roch, which is not there in the Hitzer book. Hitzer book would only looked at the top term. Then there's no scope to bring the lower terms. So when you do this composition business, because you took all the terms, that actually gave you freedom to do other things which were not obvious, you know, just looking at Euler characteristics. You can view it like that.
But finally, the commutativity is one graded piece at a time.
What do you mean? Where is the grading here?
Is there to the right?
Tangential is not a homogeneous element.
No, it is not.
That's why it's not a single graded piece.
That's what I'm trying to argue. And also, when he wants to say it's one grading at a time, no. To say something is one grading at a time, everything should be graded. Only this side is graded. There's no grading here. And you want a commutative diagram. So what do you mean by reducing it to one graded at a time?
So go there.
Of course, there is a way.
No. Graded piece.
Yeah.
Go there, look at a graded piece. That graded piece goes down to a graded piece.
What Nitin is saying is you have two elements which are sums of homogeneous elements, and I want to say they're equal. They're equal if and only if each graded piece is equal. This assertion is correct. But it's helpful to you only if you are able to take this, push it down, and isolate in some sensible way the rth graded piece. Then I can compute it that way and attempt to do it. We have no sensible method right now to do that. But I don't say it's, in the scheme of things, a bad thing. Given that later on we think these are isomorphic, this was graded. This should also be graded. I should have been able to see the grading right away. And I should have been able to do it entirely in that language. Indeed, you can. So that's the last lecture we'll see. Yeah. Yes. Yes. That's what Nitin is saying.
But he's saying this gives him more.
Yeah. It gives. Sorry? I'm going to say in the end, yes. I'm going to discuss that also later in the lectures. Yeah. Tensor Q. The original GRR didn't have Q, but doesn't matter. It's a statement in the end. Two things are equal with values in a Q vector space. They're all homomorphisms. So without loss of generality, things factor uniquely through the tensor product with Q. And so but the thing is, the F lower shriek makes sense without the Q. If there was some torsion of some kind, you could, in principle, try to understand it on this side. There you tensor with Q the moment you took the Chern character. You have no choice there. In this context. Okay. Right. So I want to just again remark, this formulation allows me to immediately say, if I have the theorem for two given types of morphisms, both these operations, I wrote it as F lower shriek, but of course, F1 composes F2 shriek is equal to F1 shriek composes F2 shriek. And similarly, F1 composes F2 star is F1 star composes F2 star. Meaning both these sides are compatible with composition. So higher direct images are essentially compatible with composition. You have to think about we have to write a spectral sequence. Spectral sequence for the composite, derived functors of the composite in terms of the, right. It's if you're familiar with the Leray spectral sequence, that's the composition where the last thing is a point. So the last thing is not a point, it's higher derivative. So there is a spectral sequence, E2 RS is R. So in other words, my situation is that I have two maps F1 and another map F2. Then RR of F2 lower star of RS F1 lower star or something converges to R F1 F2 composes F1 lower star R plus S of the thing. There's such a spectral sequence. All of these have only finitely many non-zero terms, and so you have Euler characteristics, and there's a general assertion Euler characteristics are preserved in spectral sequences. So this, let me just write that down. And you say bounded spectral sequences. Let me not explain that in detail right now. If people want in the end one of those discussions, we can try to go through all this. Or it might have been done somewhere in our literature. Anyway, you'll find this statement written in various books. I put bounded here. Without specifying what bounded exactly means, but Right, so that does require a little discussion. It's part of sheaf cohomology, that is true. Okay. So even if one is interested only in computing chi of sheaves, i.e. computing, understanding Hirzebruch-Riemann rock, you have the option of doing it by writing the map X mapping to point as a composition of two other maps and checking it for those two maps. So as I remark, any proper map in general f y to x is always factorizable. Let me change things around. Sorry. Let me go f x to y proper rather than f y to x proper, because my notes, all the later calculations, I've done it with x and y. I'll be in serious trouble if I change. Yeah, so I will. Any map can be factorized like this, where this is an embedding. Let's come back to the taught class again. Since there were some mistakes in what I tried to do last time. So indeed, we do take the power series x over 1 minus e to the minus x. This is the correct power series. And then you define Todd of vector bundles as product. So E has rank R and alpha 1, alpha R, its churn roots. Then I write product I equals 1 to R, alpha I over 1 minus e to the minus alpha. This is the correct formula for taught class. So I'd forgotten that x there, but once you put the x, that's okay. The second thing which I made a mistake is in writing the lemma of Grothendieck, Borel, Serre. I had my handwritten notes. I typed these notes kind of hurriedly in preparation. Like I missed that something should be outside and not inside. So let me write that more properly. So let me rewrite that lemma which I stated earlier. This is a lemma of Grothendieck, as exposed by Borel and Serre. This is the correct form. Last time what I wrote, instead of this, I had written Todd of E dual. That's not correct. This is the right thing. Or put it different, since this is invertible, I can put it on the other side and say CRE equals Todd E multiplied by this. And the proof I gave last time indeed proves this formula. And I was puzzled that whatever I got in the end didn't look like, because it's not correct. This is the right thing, and this is what the proof gave. Right? Let's look at the proof again. In terms of the churn roots, if I compute to the left side, I got the following expression: alpha 1 alpha r times product I equals 1 to r of 1 minus e to the power exponential of minus alpha I divided by alpha I. This is just the reciprocal of whatever was coming in the definition. So that's to clear that up. Now, therefore, let's carry on now with trying to prove the Grothendieck-Riemann-Roch by factorization. So let me discuss the proof of this one, y cross Pn to y, the easy case. And then in the second lecture today, I'll try to do the other more non-trivial case of the embedding. So proposition GRR holds for the projection by y cross Pn to y. Of course, I have also the other projection to project the space. So I'm going to use that. So case 1, y equals point. So basically I'm trying to prove, i.e. want Hilsenbrook-Riemann-Roch for Pn over the ground field. Right? We know Grothendieck-Riemann-Roch reduces to Hilsenbrook-Riemann-Roch if the base space is a point. So this is an example where the base space is a point, and therefore I want just HR. So here you kind of do it by computation directly. So the idea is K naught of P and K is generated as a abelian group by O Pn of minus I 0 less than or equal to I less than or equal to I. In fact, it's free abelian on these classes. Have we proved anything like this in the that K naught? I guess if K naught wasn't even defined, there's no question of proving it. So I have to think, can I explain this? This would follow from the Syzygy theorem, for example. Any well, has a finite resolution by of length at most time. No, but then they have many twists when you do it like that. No, I want only the twist in this range. I have to do a little work, which we'll do. Don't worry about it. So I'll come back to this. Now, Bilens is one method, but let's try to be as basic as possible. So this assertion, I'll maybe try to come up with a simple argument for this. Right now, I assumed somehow it was known, and well, anyway, I'm going to give a fancy argument later on for something. So maybe that argument will also. Okay, I'm going to do something else which is more fancy, which has y, which will at the same time prove this assertion. Okay, let me assume this for the moment. Assume you can say Bayesian, but I'm going to formulate things in terms of Castelnau-Mumford regularity instead. That's another method, but I'll do that later. So let's assume this for now, that the standard sheaves OPN of minus I, but with I in this bounded range, actually span the entire Grothendieck group. Yes? It is. I'm not using it, but it's correct. Well, that in a sense is a nice exercise. You have the Hilbert polynomial associated to a sheet, and it's easy to see the Hilbert polynomials are linearly independent as polynomial over Q. Therefore, it's of basis. Right. So let's try to do some computations. First, start with this exact sequence O Pn of minus 1 to the n plus 1 was to T Pn to 0, a version of what people call the Euler sequence. Hartshorne writes something called Euler exact sequence, which is the dual, but of course that's the same as this. Hartshorne would write it with omega and the other way. It's the same thing. This allows me to compute that Todd of Tpn. In order to, I also have to know what is the Chow ring of Pn. Apart from knowing this, I have to know that Chow star of Pn is Z bracket H mod H to the n plus 1, where Chow 1 of Pn is Z times H. H is, if you like, C1 of O Pn of minus 1 for my purpose is plus 1. That's correct. I want this to be plus, then minuses come somewhere else, and Todd will also have minus. It will all take care of it.
So you need this because you need it for a case where it's a relative case. So the specific case where it's the projected.
In my notes, I've given some discussion, certainly. But I was told that it's done, so I skipped in the lecture. Yeah, so, but, yeah. And I'm going to later on, recall various things of that kind, which I have given some discussion in the notes, but they were done in other lectures, so right now I can just go over it. Anyway, let's carry on with this. This is a presentation of the Chow ring. Notice it's the same as the presentation of the singular cohomology ring, except little h is degree 2 in that case. So that's a nice thing where, somehow the cohomology and the Chow groups are, 2 pi, yeah. No, as a group, as a ring, it's abstractly, it's correct. Yeah. So anyway, I can use this to compute dot Pn.
But that should be plus 1. OPN.
Yes, quite right. Thank you. Thank you. If it had been, yes, correct. The tangent bundle is certainly generated by global section. I have to get the Lie algebra in terms of vector field. It better be plus. Yeah. H naught of this is endomorphism of the underlying vector space. This is the, multiple of the identity endomorphism. I take global section. So I get that the correct Lie algebra on the other side, which is reasonable. Okay. So this computes as follows. This is the same as Todd of OPN of 1 raised to the power n plus 1, because Todd is multiplicative. And Todd of the trivial bundle is 1, right? So this is equal to h over 1 minus e to the minus h to the power n plus 1. But of course, when I write such an expression, what I mean is compute it, expand it out in powers of h, but then truncate h raised to n plus 1 equal to 0. So it's some polynomial in h of degree at most n. But I don't want to say what polynomial it is, just keep it like this. Let's also compute churn.
Just a bit careful because
Yes. No, I'm saying h over 1 minus the whole expression raised to the power n plus 1, which is equal to 1 plus something raised to the power n plus 1. And that was the definition also of the Todd class. Though we wrote h over 1 minus e to the minus h, we thought of it as 1 plus something higher degree terms. We keep emphasizing that. It always starts with 1 plus higher degree terms. And that expression I then substitute accordingly. This is just a mnemonic for finding the coefficients. If you like, this is the definition. This raised to the power n plus 1, yeah, whatever it is. So churn of OPN of minus I is of course churn OPN of minus 1 raised to the power I, which is churn of OPN of 1 raised to the power minus I, which is e to the minus I h. Therefore, e raised to h should have been churn of O1 by definition. So O minus 1 is e to the minus I h. Raising that to the further power I. This I is not the square root of minus 1. I is just an integer which lies between 0 and n. So what is the Hirzebruch-Riemann-Roch? What would it give as a possible formula for chi if we believe, if we want the theorem to be correct? It's supposed to compute chi, so it's supposed to give me I want to compute degree of churn OPN of minus I times Todd of TPN. Right? I compute this product and then take the degree n part in the grading and then compute the degree of that. So in other words, it's the coefficient of h raised to n in something written in terms of these things, e to the minus ih times h over 1 minus e to the minus h raised to n plus 1, whereas Kapil says we have to interpret this correctly. But remember, I'm only interested in the coefficient of h raised to n. Even if I don't, if I now think of this as some formal expression, I can forget the actual projective space and all this stuff and forget it's chowring h raised to n plus 1. I'm just looking at the coefficient of h raised to n in something in the power series ring in one variable, q power series h. I'm only interested in the h to the n coefficient, then its image in the quotient ring will be the right thing. It doesn't change the coefficient. So I might as well evaluate this coefficient in, I can even go C, convergent power series H. If I want to, work very classically, then I would write some integrals with 1 over 2 pi and so on. Let me instead write residues, but if you like integrals, you can even write it like that. So this is equal to residue at x equals 0 of e to the power minus ix, I again I stress is a non-negative integer, x over 1 minus e to the minus x raised to the n plus 1 times dx over x to the n plus 1. So I've changed the variable from h to x. I'm allowed to do. It's a purely algebraic calculation, which I can choose to do analytically if I like using this residue business, but if I think of residue as something analytic. Okay, but now because I'm in an analytic context, I can do change of variables. And I want to compute residues. So this is equal to residue. Even that I can do algebraically if I want to, but let me think of it as change of variables. Y equals 0 of 1 minus y to the, I minus 1 dy over y raised to n plus 1, where I make a substitution y equals 1 minus e to the minus x, which looks like x plus higher degree terms. Okay? And then e to the minus ix is 1 minus y to the I, and e to the minus x dx is equal to dy. And I'm using that residue is invariant under change of variables. So this is simple enough. Dy of this thing, this is a polynomial. It's just saying what is the coefficient of y raised to n in the polynomial, basically is what it's asking. I minus 1. So I claim the answer is clear. It's a small degree polynomial. It doesn't have any terms like that, except, have I done this right? I see. Okay, yeah. The power is I minus 1, if you do it carefully, okay? I claim. But I could be 0. So this could have been 1 upon 1 minus y. In which case it's no longer a polynomial, it's a power series. And that power series y does have terms of all the degrees. So therefore I get is equal to, I claim, 1 if I equals 0, 0 if 1 less than the I, less than the n. This is what came out of the Hirzebruch-Riemann-Roch formula, assuming it's correct. Now does this agree with chi? Because the Hilsenberg-Riemann-Roch is the statement chi equals some number computed by some elaborate rule. I computed that number for all of those sheaves. Does that agree with the actual computation of chi from cohomology of projective space? It does. I claim chi of Pn OPn or minus I is equal to k, the ground field k, if I equals 0, is equal to 1, chi is the Euler character, 1 if I equals 0, and 0 if 1 less than the I less than or equal to n. If you take each of these sheaves O, P, N, or minus I, 1 less than the I less than the n, all the cohomologies are 0. There are no sections and no higher cohomologies either. For example, on the projective line, O minus 1 has no cohomology at all. So it's both sides are computed and they agree. So the theorem is true by direct computation. Now let's spend a few minutes to explain why this is enough to take care of y cross Pn to Pn. This is the so-called Castellano-Mumford regularity which I alluded to. There are other ways to do it. Let's see. Maybe we have let's see how quickly I can explain Castellano-Mumford regularity, and then if there is time I'll make another comment on the lines of Bilesen. So what I claim is K naught of y cross Pn is generated by classes R. So I erase that diagram, I suppose. Yeah. I had y cross Pn to y by projection, but I also had another map eta to Pnk. So in fact, I claim if I take O, P, and K of minus I, and then take eta upper star of these guys, Castellano regularity theory, whatever I'm going to explain now briefly, says that K naught of y cross Pn is generated as a K naught y module by these classes. Okay? So I claim that if you do that, then the y cross Pn to y, now y is the variety at the bottom. Remember, everything inside was a module over the lowermost, K naught of the lowermost variety, which is in this case y. So I would have checked the formula for a bunch of generators where all the maps are module maps. So in fact, the formula is correct for any element. Making sense? I'm saying the nature of the GRR formalism, all the maps are K naught linear, right? So I have a map y cross Pn to y, everything inside is K naught y linear because y is the target variety. So the commutativity of the diagram, it's a diagram about K naught y modules. I can view it like that. And so if I have a bunch of module generators and I check the commutativity for those generators, it follows for an arbitrary element. Okay? So if I know this property, I claim I have checked it for this. The formula, once it works for Pn to a point, it works for the pullback things, nothing has changed. That I leave you to verify. So I need to prove this in order to finish GRR for y cross Pn to y. So let's see how to do this. So first of all, I claim there's such an exact sequence, 0 to OPn of minus n minus 1 goes to dot dot OPn of minus 1 to the n plus 1 to OPn to 0. There's such an exact sequence of vector bundles on Pn. So what is the basis of this sequence? It's just, I can view it like this if I want. Let's look at O, P, N to the n plus 1 onto O, P, N of 1. This is O1 on projective space is generated by the vector space underlying. I mean, the elements of the underlying vector space give me naturally global sections of O1, and O1 is spanned by those. So this map is surjective. Right? So I can view that as O minus 1 mapping to O. And then this is a surjection of vector bundle to a line bundle, I can take exterior power, causal complex, I can write. Put another way, in the polynomial algebra, of which this is the proj, I can write a graded resolution of the residue field using a causal complex. Now taking into account the degrees of the variables, the causal complex is it's a free resolution whose terms look like exterior powers of the first one, but there is a weight involved. So when you take tilde everywhere, tilde of the residue field is 0 because it's a finite length graded module. There's no sheaf and projective space associated with it, right? And then I get an exact sequence of vector bundles. However, we want to see this is a standard exact sequence of Pn. So I can dualize it. I can write 0 to OPn, to OPn of 1 to the n plus 1, so on, OPn of n plus 1.
Also puts the claim that these are generated by 1 less than equal to I less than equal to, because it is O a minus n minus 1 and the combination of that.
That's correct. That's correct. And I'm indirectly going to use the same thing. I'm going to take an arbitrary f and tensor this with f and write it like this. So I can of course take eta upper star of this sequence to y cross Pn, and I can tensor this with some f. So I'd write 0 to f, to pi upper star f. F, remember, so suppose f on y. And everything is a k0 y module. So I can use that to so let me just call O1 on the product eta upper star O Pn k O1 is O y cross Pn of 1. It's O1 of the map pi, right? Let's just use this notation. So twisting means twist by the pullback of O1. So what will the general term look like? It will look like f pi upper star f of minus I raised to the binomial coefficient n plus 1 choose I, something like that. Right? Minus I plus I. Yeah. Yes. It doesn't matter. Binomial coefficient, I can use the symmetry. So, or whatever. So the point is pi lower upper star f is resolved with finitely many sheaves which are all positive twists of f. So in order to get the class of f, it's enough to get the class of f1, f2, f3 up to fn, n plus 1. But so in order to get the class of any f, I can as well assume my sheaf f is replaced by pi upper star f is replaced by pi upper star f of a. I'm making a mistake. I can of course do this, but this is too special. I have to take f on, there's no pi upper star. It's not wrong what I wrote, but it's not enough. I have to do it with arbitrary sheaves f on the space. This is a sketch in the notes, and don't worry, I'm just doing it quickly by hand here. Take any sheaf, so any class here, it comes from a general sheaf. This sequence of vector bundles makes sense on the space. So I can take an arbitrary sheaf and tensor it by that. So that arbitrary sheaf f, the k0 class of an arbitrary f, is in the k0 classes of, suppose I have the k0 classes of fa for a greater than or equal to some n naught. That would be sufficient to get the class of this f also, okay? So I can restrict my sheaves, myself to sheaves which are sufficiently positively twisted. So k0 is generated I can as well restrict myself to sheaves which have this particular vanishing property. Because the sheaf O1 has is ample for the map pi. So any sheaf after twisting sufficiently positive has no higher direct images. The possible negative things here, though I put I greater than or equal to 0, in fact it's 0 less than the I less than the n. So the amount of negativity is bounded by n, the dimension. So f minus n twisted by something sufficiently positive has no cohomology. So I can always, if I look at sheaves satisfying this condition, then the class of such sheaves clearly generate the K0, because any sheaf I can make it more and more positive by applying this again and again. Okay. Now Castelnau-Mumford regularity let me say theory implies the following. You take TIF to be the following object. I've got a small typo in my notes there, by the way. It's pi lower star of F tensor eta upper star of omega I Pn of plus I. Just write these things down, whatever they are. Given F, I can write this. This is some functor of F. So, fact, if Ri pi lower star F minus I equals 0 or I greater than 0, then there exists functorial in F. Resolution on Y, which looks like 0 to Tn F of minus n minus 1. Sorry. No. Resolution looks like this, 0 to pi upper star of Tn F of minus n. Yeah, goes to, I got enough was it? One more. Yes, 0 less than the I less than n is correct. Yeah, that's correct. So this Castelnau-Mumford regularity theory implies that the sheaf F has a resolution by terms of this kind, where the terms appearing in the resolution are pi upper star of something twisted by minus I. And the thing I'm giving you even a formula. It's a very complicated looking, whatever it is, it's something that lives on Y. This is some sheaf on Y, cooked up in some complicated way. I'm not saying this is an obvious fact. This is the theorem. The main theorem of Castelnau-Mumford regularity is the assertion that this is correct. So just to start things off, it's saying that what is this T0F? There's no omega then. Omega 0 is just the structure sheaf. So this is just say take pi lower star F. So this map here is just the natural map pi upper star pi lower star F to F. So it's something like saying along the fibers F is generated by global section. So Castelnau-Mumford regularity theory says, because I know some vanishing of the higher cohomologies, the sheaf is generated by global sections. And then the Castelnau-Mumford regularity, the next step would say, take the kernel of the thing, take global sections, the trivial bundle associated to global mapping to F. In other words, in a family, it will be take this, take the kernel. That is again Castelnau-Mumford regularity with one better regularity. That twisted by minus 1 is again has the same vanishing, and so on. Inductively, that constructs functors. It takes much more work to write down the value of the functor equal to this. That takes more work. So, yeah. In case if we believe this, then as up to k0 y module structure, I'm saying the O minus i's, I running from 0 to n, span everything, which is what I wanted. It simultaneously takes care of the case y equals point and general y, of course, mapping everything into this box here. Yeah, I think I'll stop with this for now.
The way it is written, this is the reflex of G naught of.
Yes, but y is non-singular. So I'm taking that into account.